Here is an explanation for the answer to final exam question number 92, found on page 680 of Teach Yourself Electricity and Electronics, 5th edition. The question talks about a practical integrator circuit. Well, first of all, we need to know exactly what an integrator circuit does. And in order to explain that, the easiest way is to say that it undoes what a differentiator circuit does. Okay, so what does a differentiator circuit do? Well, a differentiator circuit takes, suppose you have an input waveform like this. It could be anything, but let's just say it's a sine wave for simplicity. A differentiator is going to take the slope of this curve at every point and assign a voltage to that slope. So if we start here, so let's just suppose that we start right here on this wave. The slope is 0, so the derivative is going to be 0. The slope here starts to go negatively, so the derivative becomes negative and reaches its maximum negative value where the slope of the curve reaches its maximum negative value. Then the slope starts to get less and less negative, returning to 0 right here. Then the slope becomes positive and reaches its maximum positive here. And if we continue on, what we're going to get is another sine wave that's displaced to the right, in this particular example, of the original. This is the derivative of that. So, let's just extend these a little bit. Extend these waves just a little bit. Time goes like this. Voltage, positive and negative like that. So this, let's call it wave Y, is the derivative of wave X. Okay, fine. Y is the derivative of X, therefore X is the antiderivative of Y. Another way to say that is that X is the integral of Y. Now you're beginning to get the idea. An integrator simply undoes what a differentiator does. Well, in the case of a waveform, a periodic waveform, that's true. But that isn't necessarily so in other types of circuits. Let's just say, for the sake of argument, that we have a DC voltage like that. The derivative of this is going to be 0 because the slope is always 0. But if we take an integrator circuit and integrate nothing, we're not going to get a DC voltage out of it. If that were true, we could have an integrator circuit sitting there all by itself without anything connected to it at all, and we'd get a DC voltage. But moreover, whatever this DC voltage is, the derivative is always 0. So not only would we get, if this were literally true, we could have an integrator circuit sitting there all by itself and it would produce a DC voltage that we couldn't even predict. It could be anything from 1/10 of a volt to 1,000,000 volts, we'd never know. Well, obviously, there are limits, there are differences between practical and theoretical circuits of this type. Let's just suppose, though, now, that what we do is we integrate this. When we do that, what we're going to get is a steadily increasing voltage. Here, if we differentiate this, we get this. We are using, just relative terms here. If we differentiate a steadily upward sloping line for the function of voltage versus time, we're going to get a steady slope, which is positive. So this is the integral of that. In a practical circuit, that could indeed be true, but how far can this go? How big can that voltage get? Well, it can increase indefinitely, but only up to a certain point. We can't, if we have a 5-volt power supply, we can't get 5 million volts if we just wait long enough with an integrator circuit. In theory, mathematically, yes, but in a practical integrator circuit, no. That can't happen. So how big can this voltage actually get? Well, it can never exceed the power supply voltage. So if this is the power supply voltage, what we're actually going to get if we integrate is this. It'll rise until it gets to the power supply voltage, or if that were negative, it would fall, and then it'll just level off, it'll saturate. So the correct answer to this question number 92, found on page 680, D, as in delta.